All right, thank you. Good morning. After this great talk about, essentially everything about deep learning, we will now dive a little bit deeper into one aspect of this, actually the word embeddings. But let me start with a few words about why the Produktmacher are talking at the Datageeks Data Day. Actually, we at the Produktmacher all share the same passion for creating great, innovative digital products. And we, at the same time, we strongly believe that from now on and in the near future, building a great digital product will mean that it somehow incorporates, it's a data-driven product and somehow incorporates machine learning and artificial intelligence. And that's why we intensified our research into this area. Today I'm going to talk about the word embeddings and our experiments with that. Why word embeddings? When thinking about data-driven products, then one very important source of data would obviously be natural language. And when working with natural language data, then the word embeddings became a standard and actually a very important basis for everything which you would later on then feed into your deep learning. So my talk isn't about deep learning, but everything creating the fundamentals and how you would feed in your deep nets with the data before. But I was really interested in what can we get out of raw word embeddings, how powerful they are, and can I simply just convert everything into word embeddings and then go for it, or are there some necessary steps? Can we improve the quality of the word embeddings? So, and this is actually also my the title of the talk, right? The good, the bad, and the ugly, or simply put, our experiments and our experiments with word embeddings applied to car data. We already heard this, and you probably all know this, but maybe a few here don't know what word embeddings are, so I will quickly say a few words about that. Before the invention of word vectors, there was one very easy way to represent text as vectors. Whenever you would need to feed them in your algorithm, you need a numerical representation, and of course you would have to convert your data, textual data, into vectors. And this is the one-hot encoding. Most of you would probably know this. Actually, the vector is the length of your vocabulary, and it's filled up with zeros and only one where the position of the referring word in the vocabulary is. Right, so I brought here an example. Actually, I think it's quite clear how the one-hot encoding is done. Obviously, the data is very sparse, but this would be the biggest problem. But the problem is that every word has now the same distance to each other. And this is really a problem because, intuitively, the meaning in words and in the language is always, there are some semantics in it, and there are words which are more related to each other than other words. And this was obviously the challenge to tackle in order to find a representation which capture the semantics and the meaning of words. I've here an example how, for example, the CBOW, which is the basis for the word to-vec, is actually calculated. So you would choose a focus word, and for the focus word, you try to predict the probability of the words in the neighborhood, like 2 words before and 2 words after. And then you go for every word, calculate the probability, or there's the other way around, GLOVE, where you do it the other way around. So giving the context words, you try to predict the probability of the center word. Right? So these are the two methods to train a model for word vectors, or word embeddings for that matter. And once you try to predict probabilities, you have a cost function, and then of course you can use a neural network. And the trick is here that simply the hidden layer is used as the word embeddings. So actually the vectors in a hidden layer are the word embeddings. Yeah, and that's pretty much it. There's one huge advantage of this. Since the hidden layer is usually way smaller than your vocabulary, it's also a compressed representation of your words, which should capture in some ways the semantics of the language. I brought here a very, very famous example where there are some vectors, so king, queen, women and princess, or woman and princess are the vectors, and then some of the meanings of your language is somehow derived from the neural network, right? So reality isn't a dimension, but it's somehow a derived meaning, which, as always with neural networks, you cannot say it's exactly reality. But for, simply put, in one dimension of your word embeddings, you would have high values for king, queen, and princess, and a low value for woman, right? Okay, and I was simply interested in this. I said, okay, somehow word embeddings are able to capture some meaning, and I wanted to apply it to data. And what kind of data? I really love car data because I think it's a very complex data set, or very complex data. When you look at natural language data about cars, then you have several meanings or layers of meaning. On the one hand, when you talk about cars and you talk about makes, then it's very emotional. It's some kind of status. It's the images you have in mind and everything like that. When you talk of a certain model, you still have some of this emotional layer, but still there's more into like generations, facelifts, functionality, body types, and stuff like that, which is all related to the car model. And then you can go one step deeper and look for the equipment or the model line and stuff like that. So giving an example, the make would be Audi, the model would be Audi A4, and then the model line would, for example, be Audi A4 Avant, which means it's a station wagon, right? And my hypothesis was, okay, somehow the word embeddings should capture some of these complex relations, right? So it said that they are able to do this. And I wanted to really look at the word embeddings and not feeding it into a deep learning network. So due to the Datenschutzverordnung, which is coming in May 2018, I won't say where I get this data from. But actually, it's all news and reviews about cars or news reviews from cars. And you can see here the size of the data set, so they are not very huge, but still it was some kind of sufficient to work with. Data set D would be the combination of all the three before. And I tried to find very different kinds of data sources for these reviews and the news. And by the way, I'm talking here about German data, right? So because I want to train my own word vectors and see whether they are able also to work with the German language and with these specific domain knowledge about cars. Yeah, so this was actually the background or the setup, and now I started with the experiments and looked, okay, what can I do with the word embeddings? How can I assess whether this works for me or not? I would like to see whether they can capture some of the similarity between makes. The hard thing about this, we will come to this in a moment. And then, of course, I trained for each of the data sets. I trained the word vectors using the word-to-vec implementation of Gensym, which is also in Python. And in order to assess the quality and have a first glance at the results, I simply extracted those vectors from the most frequent makes, which are 57, and then created from these vectors a PCA in order to have a look at it. And I will show you here the results for each of the data sets. So what was very surprising to me was these extreme outliers for Volkswagen and BMW. And also you can see here the upper right picture looks quite okay from the makes, but it's completely strange that Audi is there in the middle, right? And also for the cluster below, you have Mercedes-Benz and Maserati and stuff like that. So more the luxury makes looks pretty pretty fine, but then you have Alfa Romeo in the middle. So, okay, it's an Italian brand, but still, I don't know. Same here for next data set. Again, extreme outlier for BMW. And then you can see here everything clutters in one point, actually. But when you look at the details here, they are looking, at least in my opinion, quite okay. You have so the micro relations when you look at one spot in the picture look quite okay. So you have a decrease in price here from Jaguar, Lexus to Mini, Honda, and Nissan, right? So could make sense. Dataset C, same picture here. Not such extreme outliers, but still you have some. But here, Peugeot is next to Ferrari and Mercedes-Benz, which is obviously not correct. But here, Maserati, Aston Martin looks okay, and Kia and Suzuki, Hyundai, they are close together, and there's some distance. Again, some micro relations seem to be okay. Dataset D, as a reminder, it's all the dataset A, B, C put together, right? So this is in the combination, and we see the huge outlier here for BMW again. And just to make the spoiler, you don't going to know why BMW makes such a great outlier, because I don't know the answer. I have some hypothesis, but I didn't find it out. However, we have here, again, some nice clusters, but for example, here, when you have Peugeot and Renault, of course, you would assume that there should be Citroën somewhere, right, around the corner. So I stopped there and thought, okay, yeah, first of all, we have the PCA in between, so maybe it's because of the PCA, and how could I now assess the quality? So which one is actually the best? I don't know. And the problem with car data and the way we looked at it is there is no training data, right? So whether a make is similar to another is a gut feeling. It's not that you can really look at huge data sets, especially because we are only talking about 57 makes here. So what I did in order to somehow get an objective or a cost function is I manually created a matrix and entered my gut feeling as a similarity matrix between the 57 makes. By the way, it were a bit more and it was really cumbersome to make this manually, but I reduced it to 57. And then I had a cost function I could compare, or a benchmark, and could compare each similarity matrix against this one here. And then I created again, extracted the 57 makes from the word vectors of each data set, put them as similarity matrix, and compared it visually against my benchmark, and can see here that there are huge differences between the data sets. First of all, is that the similarities are much higher than my gut feeling was, right? So you would only say, if there's some relation, you would put in some similarity, different to the word embeddings, they usually put some similarity in everywhere and go quite high. You can see these white stripes here. This is always when the make was completely missing in this data set. And then you can see that somehow this putting all the data together goes a little bit closer to the benchmark. Next step was to look at the sum of squared errors when comparing these matrices. And here, okay, there are obviously some differences in the results. And then I tried to make sense out of it, and this is quite easy answer. It's the size of the data set. These are the number of unique words in each data set. The more data, the better the results. So not very surprisingly. However, we get into more details, and I think some more interesting results than more data, better results. So the next question for me was whether to pre-process the data or not. I'm coming from a more like classical machine learning background, and back then, before the invention of deep learning, we really had the need to really squeeze our features and extract them and do the pre-processing, and it took 80% or 90% of our time before we could feed them in the actual algorithm. And I know nowadays you put simply the raw data into the deep learning and let do the deep net the work. But I think the truth is somewhere in the middle. You really have to understand your data, and sometimes I believe you really have to pre-process your data in order to get the results you want, even if you put it into a deep learning network. And you can see here, my gut feeling was right. So I only did this for the 2 best data sets. And the second is always without stop words. So I simply used the NLTK German stop words and extracted them from the feature set, and then learned the word embeddings on the data without stop words. And it was really I would say, it improved the quality. Always compared with my manual benchmark. Then next question would be, okay, what about the hyperparameters? Could I tweak some performance when I train my word embeddings? Is there something in it? And I did some experiments with the size of the vectors. And for this task and with this data, I got the best results between 100 and 200. Dimension of the hidden layer, right? So the dimension of your word vector. Which I cannot explain this. I mean, it just simply worked better, right? And then I looked, okay, now I have this, did some experiments, and now I want to really look at the results. So how good are the predictions of the similarity of makes? And here are some findings. When I look at Skoda, which is some middle-class alternative in Germany, then similar to Skoda would be Seat, which is very nice because this is also the Volkswagen concern. Then some other makes from all over the world. So there's no certain cluster here which I cannot understand, right? So this looks quite okay from the similarity. I don't know how you feel about this, but. The same here, of course, we found the French cluster. So Peugeot is quite similar to, a few words about the methodology of the method here. I simply extracted again the make vectors and then looked for the most similar ones. Okay, so this really are the most similar ones is Renault and Citroën, which is quite nice. And then, of course, some from the German perspective, always alternatives to these makes. I'm sure in France this looks completely different. And then a cheap global player, or the cheap global players such as Mitsubishi and Dacia, which produce the most cheapest cars in the world. And then I found this, and then some other makes here. Oh, sorry, some other makes here, which are from the same region more or less, but I couldn't understand the Citroën, which is a very high similarity. And then I Googled around and found that, I don't know how many of you know this before, but Mitsubishi and Citroën have a close cooperation. They even have a common plant in Russia somewhere. So this was obviously something I learned from the word vectors, which I didn't know before. Supercars work quite well. Lamborghini is very similar to Ferrari, Corvette, Maserati, Lotus, and Bugatti, which is not very surprising, right? Then again, look at the German premium brands. We had these extreme outliers, which really surprises me is that the best similarity is 0.4, right? And this is Jaguar, which, okay, if you really want to, maybe it's for some models is a bit comparable, but it's completely missing Audi, Mercedes-Benz, and the other premium German premium cars, right? No explanation for this. I don't know. Next one, which was really disturbing, was Smart, which is the most disturbing thing was that it's very, very similar, obviously, to Buick regarding my word embedding model, and GMC and Daewoo and Isuzu. So it's completely random. So at least it looks at me like this. Maybe it's too less data, but I don't know. Okay, so these were my experiments with the makes. for me, it was like, okay, it works for some makes, but for some, I would have to do some more work, maybe some pre-processing or simply adding more data. Now, the next layer of the model, if you remember this, we had the make and then the model. I tried to see whether the word embeddings are able to capture some of the meanings of the model. And when you simply use your raw data for this, here again I choose some models, some selected models, and see how similar they are. And then you could clearly identify the make cluster, right? And that's pretty obvious because remember how the word embeddings are learned, they always look at the context word, right, and the surrounding words. And of course, when you look at in X3, for example, then in most of the times, probably BMW is in a close neighborhood to X3. So this is the most similar word, is always the make to the model. And in order to get rid of that, I did some pre-processing of the data and looked always for the model and simply replaced the model with the make and model and deleted the make if it was present. Okay? So I wiped out the BMW, which was a standalone word, and replaced it with make and model. And then this worked quite well. You can see here, at least we reduced the make clusters. So there are still some similarities here, but it's not that, and also here by Audi, but it's not that strong anymore. And when you look at some select results, the Renault Clio, Skoda Fabia, and Ford Fiesta, oh, pretty nice. Small cars, works quite well. And also here, it's not that readable. It's Ford Kuga, Nissan Qashqai, and Opel Mokka. Also quite nice. So this seems quite okay. And here, again, I did the same. I created a small subset of selected make and models, and then looked in the rest of, in the whole set of every model for the most similar ones, with one exception. Also, I was a little bit lazy, and I only looked for models which have one word, because otherwise, like for example, Mokka or Fiesta or whatever, if I would have looked at the Mercedes models, for example, which always is a combination of a word and a number and stuff like that, I would have to introduce another pre-processing step, which I was too lazy for. So we're looking only at models which have one word, and with this pre-processing. And then again, I found the results quite okay. If you look for Ford Fiesta, then Renault Clio, Skoda Fabia, and Ford Focus are definitely some inspiration, some kind of similar, to this car. The same holds for a cheaper SUV or middle-class SUV, the Nissan Qashqai. Of course, the Kia Sportage is an alternative to it, Ford Kuga as well. And if you're not that on the SUV, if it's not that important,